So today we're going to have Edmund tell us, there it is, about some recent work that he did in collaboration with Susan Wei, who is my colleague here at the University of Melbourne, and perhaps will be joining us a little bit later. We'll see. This one, yeah?
Yep. Thank you.
Cool.
Actually, is my open? Okay, cool. Okay, yep. Shall I start?
Please do, yeah.
Okay, cool. Thanks for coming, everyone. So, as Dan said, I'm going to present a joint work with Susan. She's the main investigator. I'm just helping, and here's me presenting the work. And please do ask me questions if there is anything that is not clear. I will only present sort of the main ideas, and I will go into details as requested. Okay. So the title of the work is called Variational Bayesian Neural Network via Resolution of Singularities. Okay, so there's a bit to unpack here, and I'll just run down some quick background before we start. So a quick word about Bayesian neural network, or BNNs. So usual neural network, as we are probably very familiar now, and I'm just going to represent it by a cartoon. Usually what happens is we have a fixed neural network architecture, and there are weights and biases on these network put on that network to be learned, and the usual learning method is to find a weight that minimize some loss function evaluated over the data set. L of W is the loss function, and you have xi, yi, the data set. Also sometimes plus a regularization term. So this is arguing over W. For Bayesian neural network, what we do instead is, so we look at a huge ensemble of networks, each of them having sort of their own weights. And then, so what happened in the usual network is that we have a point estimation. Coming from optimized, some optimization procedure. And the prediction is done via, so if you have an input X, and then you want to know what's the corresponding output Y, that is done by just evaluating X over that network. But in Bayesian neural network, what happened is we have ensembled prediction. So what that means is that instead, so given some input X, we want to know what Y it corresponds to, but we actually output sort of an entire distribution of prediction over Y that comes from doing some kind of ensembling. Ensembling over what? Over the posterior. So it is saying, so if every one of these weights represent a neural network and a function from X to Y. And those ones, according to the data, have some kind of loss. Have some kind of loss, and then we oops, this is doubly. So the distribution over Y is some sort is average of is average over all possible neural network with that fixed architecture. But the answer of each neural network is weighted by the posterior weight. And this posterior, of course, depends on the data. So what happened is hopefully the network that is just very, very wrong would have a very, very low posterior weight and therefore contribute very little to the answer. So let's discuss a little bit why we would want to do that. What are the differences? Well, the point is kind of that this thing has a lot more information. Well, it has a lot more information about what the possible y's correspond to an input x compared to a point estimate. So in some sense, the Bayesian neural network is good here. It's not great there for the usual neural network. What about robustness, quote unquote? So the usual narrative is that Bayesian neural network is robust, whereas the usual SGD train network is not. And what does robustness means? It kind of means that it's kind of a colloquial term that sort of range over a lot of different concepts. So it might mean that it is not it doesn't overfit as easily. So in huge network, in very overparameterized network, if you seek a point estimate by minimizing some loss function, there is a chance that you would just overfit to the training data instead of finding a parsimonious one. Whereas there are work that implies that, at least with some conditions, that if you do this kind of Bayesian learning, then there is some sort of built-in model selection or a built-in bias towards a simpler model, where simpler is measured in some specific ways related to the concept of entropy or model complexity. And the other kind of robustness that people sometimes talk about is that even just having error estimates on your y, on this output value y, sometimes means that the model won't be sort of confidently wrong. So in the usual neural network, you only get one estimate y, and you have no idea whether or not the model is saying that as a tentative answer, or it's just very confident. Whereas here you could know that what are the other possible y's, and is the neural network particularly set on giving this answer. Well, there is a massive downside to the Bayesian. Oops, don't have to spell that. That's the massive downside. So the reason Bayesian neural network, well, Bayesian method has been around for forever, but Bayesian neural network is still not a mainstream method because it is not scalable. The problem is that this integral above, or this integral is not tractable. If you want to produce this estimate, it's it's not tractable for high dimension. So by high dimension, so if you want to do numerical integration, something like 5 or 6 dimensions, so neural network with just 1 or 2 node, it's already hard. Well, the alternative is Markov chain Monte Carlo to do this MC-MC integration, but that is also not tractable for the modern network size, which can go from hundreds of thousands to millions to billions to trillions. MC-MC sort of, well, it's better than doing numerical integral, but something like 10 to 20 dimensions, it's already starting to struggle. Right, so okay. So what are the remedies then? So we have a problem. So P of W, this distribution, well, I'm writing the density, but really it's the distribution that we care about. Integrating against this distribution, finding its mean or finding its spread, etc., is intractable. And difficult to sample. Well, what possible remedies do we have? So one method for doing similar things to neural networks, sort of method that is Bayesian in spirit, would be something like deep ensembling. Deep ensampling method. So the idea is that we acknowledge that we are not doing full posterior averaging, but we're doing some sort of averaging where we are averaging across guesses of the model parameter that are high posterior likelihood. Well, usually what that means is that people will train the neural network for with multiple different initialization, with different a lot of things, right? Different learning rate, a lot of things, so that it is some sort of sampling from something, maybe not the posterior, maybe the posterior. And then when we want to generate an inference Y for given input X, you just push X through all those networks and then take the average. What we want to focus on today is another family of method called variational inference method. And this is our focus today. So so to set up the problem, in general, we want to estimate some probability density P of W. So in our case, this P of W will just be the posterior. What we do in variational inference is we propose a variational family. Denote Q. Whoops. So this family is a family of distribution. Q is a distribution over the model weights, the neural network weights, indexed by some its own parameters. So now we have two kinds of parameters. Now we have the neural network parameters, and we also have theta, which is known as the variational parameters. I also apologize that in this seminar we usually use Q to be the true distribution. It is not in this context. Q is the variational family. So what does the variational family do? We want to find some member of the variational family, call it theta star, that minimize the quote-unquote distance to the true to t, to the distribution that we're approximating. And this distance, well, it's not quite a distance, but it's a KL divergence. So we want to minimize the KL divergence between q and whatever distribution we are approximating. Okay, and finally,
here you have in mind that this PW would be, for example, the posterior from some sample, right?
Correct. So this, I'm setting out this in general, but in our problem, P of W is the posterior. Yeah. And finally, we replace anything we want to do with P of W with, so replace averaging. So things we want to do with W, things we want to do with P is, for example, making predictions, averaging over it, or making uncertainty estimate and so on, but replacing averaging over P of W by Q star of W, which is, I'm just shorthanding that as the member of the variational family that minimize the distance to P of W. So just a pictorial picture, maybe we have this this variational family, and then there is this Q star, and P might be, P is usually outside of this family. Why is that? Well, why do we want this setup? This setup would be useless if there is no additional property we demand of this family. And the things that we demand of every Q in here is that, so we need every distribution in this family to have easy to compute likelihood or log likelihood, easy to compute Q of data, in other words. We also want easy to sample from them. And usually we also demand that this expression here can be optimized using first order methods. So for example, optimize using SGD. Okay, so the first two demand is very restrictive because most of the time a lot of computationally effective family is actually a lot of natural occurring posterior distribution and naturally occurring high dimensional distribution that does not have those kind of properties. So this field becomes one that devotes itself to designing a good family, designing good optimization methods, and trying to figure out the kind of balance to strike between easy to compute and minimizing this distance, basically minimizing the distance between P and the best in Q.
You said it already,
That's
but
the question?
Yeah, maybe I'll just spell it out even more clearly, since the notation is very similar to what we usually have, but somehow very different. So usually the KL divergence is between also Q and P, but the integral is over X rather than here being over W. So there's, and I guess in that picture often we're drawing like the true distribution being close to some model, but here P is not the model, the same letter, but it's standing for the posterior. So we think about the model as being a distribution over X, and then we're trying to get it close to the truth, which is also a distribution over X, but here it's, well, it's kind of X has become W in some sense. So now we have distributions over weights, and we're trying to match one by some family of now the Q is kind of the class of models in some sense.
Yep, I'm trying to match the notation of the paper. There's another thing that I'm sweeping under the rug. Well, I will explain in a moment, but notice that in the usual notation, we have the thing that the true thing on this side of the KL divergence, and the approximating thing on the other side. The reason for that will be apparent later on. And KL divergence is not symmetric, so that actually makes a difference. Okay, so let's discuss some theoretical property of this setup, just some really high level theoretical consequences that needs to be considered when using variational inference. So the optimization problem is the following. We want to minimize over the variational parameters the KL divergence between the approximating family and the posterior distribution. So I'm substituting P of W to be the posterior now because that's what we are concerned about in Bayesian neural networks. And actually, this is equivalent. How do I write equivalent? Okay, I'm just going to do that. This is equivalent. This optimization problem is equivalent to maximizing over a quantity called elbow. So that is called evidence lower bound. Explain the name in a moment. So what is this elbow quantity is equal to, actually let me explain the name first. So evidence should be familiar to a lot of us. So recall that the posterior distribution can be written in the following form, which is 1 over Zn e to the negative nkn w, where now all the notation here are standard singular learning theory notation. There is, I forgot the prior. Kn is equal to negative 1 on n. Okay, P true, the true distribution now is the true distribution over X over P model. Right. And Zn is the model evidence that we are familiar with. I'm going to work with the normalized version of things, so I won't bother making that distinction. And so this quantity called evidence lower bound is related to this evidence. But really, given our context of singular learning theory, I think it's a little bit of a misnomer, because recall that we have another quantity called the free energy, which is just a negative log transformation of the evidence, which is kind of a more theoretically easy quantity to deal with. And the reason I think this is a misnomer is because this elbow is equal to the okay, I'm going to write out the expression because that's important. Right, so it is equal to this expression, which we will define as the variational free energy but this variational free energy is, well, it's not like we have, instead of having a fixed posterior distribution, this variational free energy depends on which approximation we are evaluating it on. Okay, so this quantity is called evidence lower bound because, sorry, it's negative this free energy. So the expression here is just saying that the things that we are evaluating in here is e to the e to the evidence, e to the negative free energy, which is the evidence, but for the variational free energy, variational family, and the standard theorem from variational calculus would tell us that, well, this free energy is just always going to be bigger than the actual free energy if you use the actual posterior distribution, and therefore implicitly this is like the evidence VB. Yeah, so the elbow is a lower bound to the actual evidence. Just, I'm not going to write it. Okay, the expression of this optimization objective is also interesting because it involves this term, and this is why we swap this to position, just because we want to take expectation over the approximating distribution instead of the intractable posterior distribution. So to do optimization over to do the optimization to maximize this elbow term, so usually we do gradient descent, and at each step of gradient descent we need to estimate this quantity, this elbow quantity, and to estimate the derivative at the current point, which means that we do that by computing this expectation, which is approximated by taking samples from the current Q theta t, and that is by construction it's designed to be easy. Question?
Yeah, I have two. So I guess I can think about, if I look at the free energy formula, that's a logarithm of an integral, and I could just be brave and move the logarithm under the integral sign, and then I get something that looks like what you've written there. Okay, so what justifies that? Of course, it's not equal, but and secondly, I don't see immediately why minimizing this KL divergence is the same as maximizing this quantity.
Right. Okay, sorry. That's just okay. That is a boring calculation from that to that. Do you want me to repeat that calculation?
No, it's okay. If you just say it's some calculation, that's fine. So
yeah, it's really just write out the expression and then noticing that there are terms that doesn't depend on theta, and drop that, and that's your elbow.
I see.
Yeah. And also another important thing to mention in regards to your question is that variational calculus not only give us this inequality, but it also say that if we manage to find a Q star that is equal to P W star, then well, if we go back straight to the original definition, then the decay divergence is 0, and hence Fn VB is equal to Fn, and the elbow is actually equal to the evidence. So that it at least have the what is that? The reflexivity of a property of the metric, even though it is not a metric. And this quantity this gap between the approximating the free energy of the approximating distribution and the actual free energy, well, it's called the variational gap. It's a function of n. Well, it's actually a function of n and which member of the family that we are using for the approximation, but we make it a property of the entire family by taking the optimal distribution. Okay, so this is the comment just now is just saying that this gap is equal to 0 if there exists theta star such that q star is equal to p. Right. Okay. Now let's go back to the first board, because now I want to talk about. Actually, let me.
Like, I have a question on that board.
I think Ben had a question about the previous board.
Too late for another
Yep.
on that previous board.
Okay. Yeah.
The sense in which, like, FPB is greater than or equal to Fn, you said because of the standard result in variational calculus. The sense, when I think of variational calculus, I'm thinking sort of, a functional integral, an integral that's a function of some functional form, if you like, and differentiating with respect to that functional form, and this is very vague. But anyway, so am I to think of not fixing the family of Q, but actually varying over all possible Qs in that inequality?
Yeah, you're right. So I shouldn't even, like, in the setup that I mentioned, I shouldn't even mention calculus of variation, because I'm actually proposing a finite dimensional family parametrized by theta. So it's really but you are right. The general statement there is that for any other distribution that is not equal to the posterior, this quantity that you calculate is just going to be greater than Fn, than the actual free energy.
I see.
So it's yeah. So it is. So if we go back to just the original KL divergence definition, it's kind of the by construction of the KL divergence, and sort of KL divergence is constructed to have that property. So this quote unquote theorem is really it's only a theorem and not a tautology if it is about the evidence lower bound. Yeah. Okay. Nice. Next, I want to talk a little bit about this, where singular learning theory comes in. So regular versus singular. Okay, let me talk first about regular. What happens in this setup for regular, by just recalling some theorems that we know. So for regular model, what do we know? We know that for any true distribution, writing full sentence. For regular model, for any true distribution, P true. Okay, by any, that there's some restriction of regular smoothness and stuff like that. For any true distribution, there exists a unique W node in our parameter space. be broken down as notation, such that the DKL between P true and P of X at that parameter is minimized. And regularity, almost by definition, means that well, it means that there exists this global minima is a most critical point, and therefore has a coordinate in which it is in which the log likelihood is sum square, and that imply that the posterior converge as n goes to infinity to a Gaussian, convergent distribution to a Gaussian, centered around that point. So, so this it's kind of a powerful statement that say that this is sort of a demonstration of how restrictive a regular model is that just for any phenomena out there that you want to study, and if you're using a regular model to study it, then okay, not just everywhere, not just at W0 at the global minimum, just any minima that you're studying, that you will have a Gaussian center around it, center around that local minimum. Which means that if you want to do variational approximation of such a posterior, well, just use a Gaussian family. Use a Gaussian family and match, and also the regular also implied that the maximum likelihood estimator is will converge to, this is asymptotic consistency, will converge to, will actually find the actual minimum. So for regular model, we should just use a Gaussian family and center it around the maximum likelihood estimator and try to match all covariance. Well, the matching covariance is not that easy, so that's another thing. But it's just the situation with singular model is much more different. So to illustrate that, let's go back to the first board. Okay. So in the first board, there is a diagram there where we are plotting the posterior distribution, the contour of the posterior distribution, not normalized, for a singular model. And it is a singular model because, let me just write what the model is at the bottom. So the model is a regression model with parameter A, B. So the x-axis is A and the y-axis is B. This is just a 10H regression model. A 10H of Bx. Okay, that might be too small. So I think this is a example that a lot of us have seen. The set where things are not identifiable. Well, every point is actually not identifiable, but the set with a singularity is the coordinate axis.
It's too small for me to see, but is it perhaps y minus a tan hbx all squared?
That is a really good point. Totally right. That's correct. Okay. Yeah. So I should just write. So this is y is equal to a tan h of x plus Gaussian noise.
Bx.
Okay. Cool. Bx. Yeah. Thank you. Cool. So let's look at the bottom row first. In the bottom row, we have a situation in which not only is the model singular, meaning it's not identifiable, the true distribution that generates the data is, so W0 is at this point here. So it is on the axis, which means that it is actually on, which means that capital W0, the set of true parameters, has the singularity, right? In this case, if you're looking at the posterior distribution with dataset size equal to 50, well, it doesn't look like a Gaussian. Even if you crank it up to 5,000, it's never going to be Gaussian, right? But in the first row, though, that true parameter is away from the set where it is where W0 has a singularity. And in fact, it is the most critical point. And you can actually find locally sum of squares representation of the log likelihood. Problem is, at n equal to 50, it still doesn't look Gaussian. At n equal to 5,000, it still doesn't look Gaussian. But if you crank it up enough, this tail distribution actually will sort of just get less and less relevant until everything is sort of concentrated around this. So it's a very, very degenerate. So it's like if you zoom in by just sampling more, then it will become this kind of it will become Gaussian like that, and all the inaccuracy away from 2 or 3 standard deviation just doesn't matter anymore at high end. But this convergence is very, very slow. The reason is that there is a actually I sort of cherry picked this example on top where the situation is for this particular data set. So recall that the posterior distribution itself is random, because if you draw a different data set, it will change. And I cherry pick an example in which the maximum likelihood is actually here, right? That's kind of so this model has is non-identifiable. This point is the same as this point, but it's not the same as so it has a 180-degree rotation symmetry. But it's actually sort of the maximum likelihood is very, very far away from the true parameter. And something that contributes to this kind of behavior is because for low n, the axis is kind of a reasonable approximation to the data. And we know from singular learning theory that for a hypothesis that is singular, it has much larger fluctuation, functional fluctuation, or called singular fluctuation in that, which means that this the hypothesis represented by this origin function can cover sort of a lot more possibilities than the non-singular one can. Right. All of that is to say that the variational problem for singular posterior is different. It's much more. It's richer, and it's a theory that actually requires lots of that in practice it requires lots of engineering thoughts to approximate
that the
posterior like this.
Sorry.
Mm-hmm.
You're not saying that the posterior actually becomes Gaussian asymptotically. You're saying that it's just well approximated locally around the true parameter, right?
You mean in the top row case, right? In the bottom row case,
yes.
it's just never Gaussian. In the top row case, if you crank n up to very, very, very large value, then sort of we know that as n becomes really, really large, a parameter that disagree with the data a parameter that produce output that disagree with the data a lot simply doesn't matter. Like the weight, the posterior weight, that just becomes very, very small, right? Which means that we only need to look at a very, very small neighborhood of comparing the posterior to a Gaussian around the true parameter. We only need to look at a very, very small neighborhood. Both the posterior is very concentrated around W0, and the Gaussian at that level of n will be a Gaussian with a very, very narrow variance, which means then they match. The posterior still have tail that is not Gaussian, but they don't matter anymore because the weight of their weight is so very, very small.
Right. Okay.
When n is large, yeah. The cartoon picture in my mind is like if that's W0 and the true posterior might have like so wiggles, and then as n becomes very large, it becomes like that. So it's well approximated by the non-wiggly bits, because most of the approximation cares only about that neighborhood. Does that make sense?
Yes, I mean, when the regularity being identifiability plus, non-degenerate Fisher information matrix means that you can do a quadratic bowl expansion, Taylor expansion kind of thing around the true parameter, and the sharper it is, the better an approximation it is. And so I'm completely with you there. I just thought for a moment you were saying that that all posteriors somehow literally become Gaussian, sort of central limit theorem style, which I didn't follow, but I don't think you're saying that.
No, I'm not saying that. Yeah, I'm saying like in the bottom row case where the W0 live in a singular set, the posterior is never even with that effect that I'm talking about. It never becomes a Gaussian. And what does it become though is my next point. Yeah.
But in the regular case, it does.
Sorry.
Right. I mean,
Sorry.
Russell's
in the regular case,
in the regular case, what?
Sorry, go on. In a regular case, if your model is everywhere identifiable, in the regular case, so in a singular case, there is distinction between if your true parameter is lying on a singular set or away from it. In the regular set, in a regular case, there is only one possibility. Everywhere, for whatever true distribution, you have a quadratic approximation near your minimum point. In a singular case, then that is not true.
Yep, I agree.
Yeah. So
maybe we can move on. I don't know. I feel like I'm dragging us down.
I can. No, I'm happy to talk about this afterwards.
Yeah, maybe the end.
Sure. So what does happen in a singular in a singular case though, because we are in the singular case in neural network deep learning. So in a singular case, we know from SLT. This is related to your question in Discord, Russell. I'm using singular in the sense that it's both. It includes both regular and strictly singular cases. But anyway, from singular learning theory, we know that the actual free energy has the following asymptotic expansion. I've already normalized my quantities, so I'm going to sweep all the normalization under the rug. Okay, so from SLT, we know that the free energy have the following asymptotic expansion, where this quantity is the RLCT, as we know, and that's the multiplicity. And furthermore, the generalization error which I forgot to define just now, but we let me just define verbally. So the generalization error is just the KL divergence between making prediction. The KL divergence. So if we make a prediction using the full Bayesian model averaging, that will produce a distribution of predictions. But compare that to the true distribution, there is still some error because we are not at the true distribution. So the KL divergence between those two distributions is the generalization error. Well, we know that the expectation over this generalization error is equal to the increase in free energy. This is a crucial relationship. And this is only true if we are doing prediction using the full Bayesian posterior, not any approximation to the posterior. Then the generalization error have this very convenient representation. And from that, it implies that this is equal to lambda, has asymptotic expansion lambda on n plus smaller order term. And crucially, that lambda and that lambda are the same. Now, the problem with variational method is that we don't have the theoretical problem. We don't have such a relationship. We don't have this relationship between if we use the distribution we use to make prediction is not the full Bayesian posterior, but using a approximate one, then this relationship breaks down. Then we can, which means that the asymptotic expansion of the variational free energy needs to be decorated. I'm just going to write smaller. And the observation is that lambda VFE for the learning coefficient of the variational free energy is not equal to the coefficient, the leading coefficient of the generalization error, for variational generalization error. Okay, let's represent this with a cartoon. So singular link theory sort of clarifies some relationship here, which is we have that plot. This is a kind of cartoon representation, not claiming anything quantitative. So let's say we have lambda here, the RLCT, and from the discussion just now about the calculus of variation inequality, we know that the elbow and therefore the variational free energy is always larger than the actual free energy, which means that its coefficient, its asymptotic coefficient, have to be larger as well. So it's to the right. But where does lambda VGE go? Where does the coefficient of the generalization error go? Well, actually, let me point out that this place here is the asymptotic, is a leading order approximation of the variational gap. the generalization lambda VGE can be in one of these three places. Where if your in this situation, in here, this means that lambda VGE is smaller than lambda VFE. Here, lambda VGE is greater than lambda VFE. So in the middle situation, it means that even though your approximation is not as good as you want, meaning you actually you never got to approximating the full posterior, but if you use the approximating posterior, your generalization error is not hurt by lambda VFE not being very close to lambda. So this is kind of a good case. This is a bad case, right? It means that if you figure out your lambda VFE, your variational free energy, that is no guarantee that the generalization error has the same asymptotic efficiency typified by this coefficient. This case, though, this is very, very good. It means that replacing your the actual Bayesian posterior with the variational approximated distribution actually made for better prediction. You can imagine a situation in which you design a family that is literally at the true distribution, which means that there's no optimization going on, and the generalization error is just zero all the time. So the lambda VG is zero. That could happen, but it depends on your variational family, which leads to the second point, which is that all this is different for different. This cartoon could have different configuration for different variational family, say Q1 and Q2. We could have configuration. So let's say the lambda are still the same because we are learning learning the same phenomena, the same data generating distribution. The generalization gap could be different. So we could have lambda VFE here, and another model in which the generalization gap is huge. Now, there is something that Susan noticed in the literature, in that people generally don't distinguish between these two kind of effect. Is there a question?
Oh, sorry, I just unmuted myself. I don't know if that creates some weird noise.
Oh, that's okay. Hi, Susan.
Yeah. Oh,
There's a little bit of
I just
feedback.
wanted to say that's not the generalization gap. This difference between lambda and lambda VFE.
Yeah, yeah. So my verbal description just now, that is the leading coefficient of the generalization gap. So let me put it in quote.
But we don't want to confuse people and have them think that's related to the variational generalization error, right? Like lambda VFE minus lambda is just kind of the accuracy gap in doing variational inference.
Yeah, it's something like that, right? It's asymptotically equal to that.
Sorry, I think I'm still very bad at ROBLOX. How do I know which board is currently the
Click
main one?
orb cam at the top of the screen.
Sorry, yeah, there used to be an orb cam button. Now it just says pockets, and then there's an eyeball.
Oh, you need to attach as listener. Can you see? If you look around over there where Ben is jumping, yep, you should see attach as listener.
If only you were 10 years old, you'd be.
That's right. This is for school children, isn't it?
Awaken the inner child, Susan. And then you should see Orcam at the top.
No, sorry. Yeah, I mean, I didn't mean to really interrupt, except just that this lambda VFE minus lambda is just the accuracy of the variational approximation, whereas the generalization error is really like a downstream error when you use the approximate posterior as part of your posterior predictive distribution.
Yep. Yeah. So yeah, I hope that was clear just now.
Technologies. Yeah.
Yeah. So I was saying, so lambda BGE, the generalization error is if you substitute your posterior, if you make prediction instead of averaging over the posterior, you're averaging over the approximating posterior, then you get a generalization error, and the asymptotic behavior of that is lambda BGE on n.
That's right. That's right. Yeah, that's right.
Yeah. Oh, sorry. The red part, the red part is meant to represent lambda VFE minus lambda, not lambda BGE. Hopefully, that was clear.
That's right. Yeah.
Yeah. Okay. So there is also a situation in which you might have when you try to do a variational this variational optimization, you find an approximating distribution that is very close. It's very close to the true posterior, meaning the gap is small, as in the first variational family, and the gap for the second variational family is large. But that sometimes doesn't mean that you might have better prediction in the first case than the second case, because the position of the generalization error coefficient might be something like that. Might be here, the other one might be here, right? So in which case, even though in the second case the gap is larger, but the generalization is better. So this is still an open problem. What is the relationship between lambda VGE and lambda VFE? Not having that relationship between generalization error and the free energy, as with the full Bayesian case, is not ideal. And at the moment, this is still an open problem, and it's only studied at a case-by-case basis for now. So,
sorry, if I can just interject a bit. So thanks, Simon. This is a really great explanation. It's just as someone who uses variational inference in the real world, I can say that one of the main challenges of using variational inference is that there is no good way of finding out if you've done a good job, right? So you have your variational approximation to the posterior. It's really not clear how to know if you've done a good job. The only way that I've seen reliably in terms of assessment is just to draw MCMC samples and then take that as the ground truth. But this is not a good evaluation tool, because if you bother to spend the time and resources to do MCMC, then forget about variational approximation, right? So that's not really a practical way of finding out if you've done a good job. And what a lot of people in variational inference, they've already noticed that maximizing the elbow, which is the same thing as minimizing this red gap, even if you do a good job, the generalization error downstream for the variational approximation could be really poor, as measured by the test log likelihood, which is another way of saying this GN. That what Watanabe calls GN is simply the test log likelihood. So yeah, there really is a big gap in the practice of variational inference. We optimize using one criterion, then we assess using another one, but it's not clear that your optimization criterion leads to any control of the criterion that you actually care about. So understanding this relationship between these two lambdas I think is quite interesting for the practice of variational inference, and could be a, just a good contribution of what SLT has to say in terms of practical matters.
Is there any task? Yeah, it's an open problem. I want to ask, is there any task in which so in deep learning, it seems like the test logs is almost the be all and end all of downstream performance. But there are situations that is where people want to use variational inference. Are there situations in which are there tasks in which the approximation gap is more important than generalization loss? For example, I would think the variance estimate would be more related to VFE than VGE.
Yeah, I know exactly what you mean. It's like controlling this gap, this lambda VFE minus lambda, even if it doesn't control this downstream prediction, are there other quantities it controls, right? Meaning we could look at the difference between the moments of the true posterior and the moments of the approximate posterior. So unfortunately, I think the answer is no. Like even controlling this gap in the red, it will not control the error in the mean or variance approximation. There are actually good counterexamples where you can do very well minimizing this gap, but then your mean and variance approximations are really bad. So a lot of this could be an artifact of the KL divergence. So everything that you're presenting here is for the KL divergence, right? There are other divergences to use, and I think if you use something like the Wasserstein distance as a variational objective, I think that does provide you good control of mean and variance approximation, but not scale.
Yeah, the kind of meta lesson here is that we kind of want to just, what is the actual downstream task that we care about? Design metrics that we optimize for that. The general sort of variational inference theory has been concerned about distributional matching, which need not be best for every situation.
Yeah. No, there's definitely a disconnect between what we optimize in variational inference and what we actually care about. But what we really care about is hard to optimize. So this is very common, right? You really care about something, but you can't actually optimize it. So you use a proxy and you hope that optimizing the proxy leads to a good optimizer of the thing you really care about. The variational inference that you're presenting here in the context of Bayesian neural networks is actually probably not the most prevalent application of variational inference in modern deep learning, right? Like it's more often that you see variational inference as part of like a variational autoencoder, and there you're just kind of happy if the things that you generate look good. This is rather subjective, like it does look like a cat, right? It looks more like a dog, and you're happy. So.
Anyway. My comment before in which like variational inference is used in sort of parameter estimation context, for example, estimating the mean level of cancer cell concentration, or DNA concentration, or something like that. In that case, we will care more about the parameter, meaning that W matching, than we care about prediction. In that case, we will actually care more about VFE, the gap being small, than the prediction being good.
That's right. Yeah.
I will move on because I think I might hurry a bit for the last few things. So in the interest of time, let me summarize a little bit. Previously, there's a work using singular learning theory. So SLT gave us the first main theorem is in SLT, the main formula one, says that that Kn function has a standard form, but to get to the standard form, you actually need, you actually need with some very null hypothesis to apply resolution of singularity and G's resolution map. In that case, you get Kg after pulling back by the resolution map, you get this normal crossing form. And the second term, this term is a Gaussian process, converged to a Gaussian process. So it's kind of has a bounded behavior. And for the rest of this talk, I'm just going to sweep that under the rug because it has a 100n term, and it's the first term that determines leading order behavior. What that means is that to go back to Russell's question earlier, is that in the singular case, we don't have asymptotic normality. We don't have posterior converging to Gaussian, but what we do have is this posterior converging to something to a standard form. So using this formula here. The resolution map is a simultaneous resolution of K and the prior. So the prior is also in normal crossing form. Right. So that's the standard form of the posterior. And there's a previous work by Bhattacharya group that uses this fact to as an inspiration to design a good variational family, meaning we want to design a family. Recall that we want to design a family that that is easy to optimize, has the best member is close to the posterior, and it's easy to sample from. And that means that the easy from sample from part. So usually there's a if your distribution is completely factored, so it's mean field, then it is easy to sample from. And the design family inspired by this standard form is this form. So it's looking at this and say that let's assume that instead of its this part is already factorized. Let's just factorize that part. Assume that it is factorized. So it's equal to u to the 2k1 times u1 to the h1 multiplied by multiplied d factors, where d is the model dimension. Right. So this is a mean field family, and it's a mean field where each component of this factorization is a gamma distribution. Well, it's a generalized gamma distribution. The computing the normalizing factor is involve a gamma integral, but not quite a full gamma integral. Is a truncated gamma integral. So using lots of properties of special functions, particularly the gamma function and the beta function, we can it was proven that the variational free energy, so which is a proxy on how close the family can approximate the true posterior, is where that lambda is the RLCT. So what this means is that if we use this family and manage to find the optimum, then we have at least matched the leading order term of the free energy. For recall that the free energy is negative. That, which means that the gap at least doesn't grow. We at least kill off the leading order term, which is the log n term. Right. I won't go to the proof that. Now, the problem there is that this assumes that everything I wrote on the board there is using the coordinate u, in which the posterior is in the standard form. And that relies, that is after we have reparameterized our model using the relationship W equal to G of U. So we reparameterize using the resolution map. Well, I think most of us here already know that getting a resolution map for a simple model is hard, let alone a large neural network model learning a non-trivial true distribution. So we don't actually have standard form in the wild. What we Susan's proposal is to the resolution function is a function. We don't know what the function is, but let's just stick a neural network there and ask the neural network to learn that function. So the proposal learn G using a neural network. I think it's more like that one, G inverse. Recall that the resolution function is an isomorphism away from the singularity, so away from a measure zero set. So which means that we are effectively constructing a new variational family, which is that O family, but then pulled back by this G function. So the new family is G push forward of the family just now. There are some other parameters of that family just now. There's beta, k, and the RST. So the relationship here just means that that normal crossing coordinate is given by pushing the usual coordinate through this capital G function, which is a neural network. And this G function has the property that it is invertible almost everywhere. So this, in fact, is a normalizing flow architecture. So normalizing flow is a popular a generative deep learning type architecture, in which the goal is to transform a very simple distribution to a very complex distribution, where the complex distribution is the distribution that we want. And the way it does is, so for example, we can start out with a simple Gaussian distribution, where that Gaussian is very, very easy to sample from, very, very easy to generate data, and then generate sample, and then move it across via this transformation and get some really wacky distribution. Right, and there's some requirements on this architecture so that computing this transformation and optimizing it is easy. And that's the kind of the main constraint of what kind of architecture you can put on G. And in the paper, we are using something called the affine coupling architecture, which you can explain afterwards if you're interested in. So this setup I'm drawing here is the usual setup in which people usually have a base distribution, which is a Gaussian distribution, and we and then learn this G to approximate real-world distribution. What we are proposing here is that instead of using Gaussian as the base distribution, we instead use a generalized gamma distribution. And go into that. So instead of doing that, we are doing that. Okay, I'm going to spend the next few minutes discussing the result of this. Then could you put on some board the pictures, if that's possible? We might need to move to a new set of 2 boards. Hello, Dan, are you there? Dan might be AFK. So there's a few more pictures that describe the result. And hello, Dan, is that you?
Yeah, I'm back. Sorry, I had to step out for a second. Shall I put up the diagrams?
Yes, please. Maybe we can move to a new set of board.
Yep.
Sorry for the trouble.
No, there was an emergency where Russell's best friend has come over and needs the Nintendo setup, life or death. So I had to. Sorry. Let me see if I can get that on.
So while Dan is putting it up, I should clarify that I have stripped all annotations. So it's just hopefully you won't accuse me of bad science for not annotating my axes and so on.
The graphs go up and to the right. Be impressed. Accept.
Yeah. So looking at the first board, that's that's a bit to annotate here. So we did some experiments on the setup that we mentioned. So the high level goal is to compare. So we have the usual setup is using a Gaussian based distribution, push it forward to learn a complex distribution. And we are proposing using a different base distribution, which is the generalized gamma inspired by singular learning theory, inspired by main Formula 1. So we are comparing performance of different base distribution. Another variable to vary is the expressivity of the push forward, the normalizing flow neural network, the G of theta neural network. I really shouldn't use data. I've overloaded data. So what happens here is that the red series is Gaussian base distribution, and the green series is generalized gamma. And these different plots are for different true generating function, data generating distribution, true distribution. Right. So the top one I think is a singular model. Everything here is a singular model. So remember that our high level goal is to, given a neural network, can we do Bayesian inference over the weight of the neural network? And the method that we use is to use a variational inference method, and that we main formula one, it means that we are using a normalizing flow to approximate the posterior distribution. Quite a bit of level jumping here. So there's so.
And then I
So
wonder if
G of
the details of these graphs is maybe a bit I don't know, a bit much for everyone here. Maybe we can just give a summary. I mean, so we're just trying to compare the two base distributions, right? If you didn't know singular learning theory, you would just use a normal 0, 1. That's what everyone uses in the normalizing flow literature. But because we have this cute little insight from SLT, we're going to use this generalized gamma. And then we're going to push this base distribution through a neural network, an invertible neural network with simple Jacobian. But so the thing is, if you let this neural network be extremely expressive, there's going to be no difference between the base distributions, or between any pair of base distributions. So the experiment is kind of set up so that you don't allow yourself to be very expressive, so then you can isolate the effect of the base distribution and see if the generalized gamma one has experiences a performance boost. And the conclusion is, at least based on the experiments that we've done so far, the answer is yes, you do get a boost by using the generalized gamma. And by boost in performance, I mean just I get a higher elbow, meaning I get a lower lambda VFE. But then when we switch to the generalization landscape, then yeah, there's a lot of tricky parts there because of what Edmund has explained before.
Summarizing what Susan said. So what that means is that the green lines, the one that use the generalization gamma on the left hand side here, which is plots for the free energy. The green line is lower for a lot of cases, except here. But there's a problem with comparing across different expressibility. The network that try to mimic the resolution map that have different expressibility. But going from the left to right, where the right hand column is plotting the generalization error, we can see that, for example, in the first row, even though the green always wins out in terms of having better approximation to the posterior, meaning lower free energy, lower variational free energy, it doesn't mean that it is better in prediction. The next two chart is really sort of more of the same conclusion, but for more different, more configuration of experiment. So I think I will end it there. Sorry for going a bit over time. If you have any questions, please ask. Happy to discuss.
So there was my quagmire from earlier.
Yeah. So
which is low priority. Yeah. That's my hesitation right now. But we could go.
Sure.
So my question is it are you saying that for a regular model, asymptotically, the posterior becomes Gaussian?
That is correct. For a regular model learning any data generating distribution, the posterior converge to a Gaussian when n get large enough. That is a theorem.
Okay.
Right. But for singular model, For a singular model, there is sort of two situations. Situation one is where even though the model is singular somewhere, so there exists true distribution in which the optimal distribution has singularity, and there is another case. So in that case, in that true distribution is singular case, you don't have the quadratic approximation around the true distribution, which usually give you Gaussian, which is the necessary condition to get you Gaussian, right? So that's the if you want to walk back with me to the board. So that's the bottom situation in this graph. So in the singular set is here, and the true distribution, the distribution that generates data lies on that set that has singularity. So in that situation, no matter how high I crank n, locally around that point, it's never going to be Gaussian. But on the top situation,
and so the Gaussian,
go on.
Sorry, go ahead.
In the top situation.
The lag is killing us, isn't it? Okay,
I know.
I will now stop speaking for a long time, and you go ahead. I'm not going to talk for a while.
Okay. Okay. So the top situation is a situation in which there is actually a good a local coordinate in a very, very small neighborhood, so a neighborhood that doesn't cross that, such that the surface here has a Samuel square form. So this is actually a most critical point, which leads to, if you crank n high enough, these tails will sort of shrink towards the tails becomes less and less important for the approximation. And if you zoom in enough on that point, you get a Gaussian distribution. Does that make
so
sense?
the Gaussian for finite n, for finite but large n, because it's regular and so the non-degenerate Hessian and all that, you have a Gaussian approximation, and that approximation becomes, so in the limit of infinite n, it's an arbitrarily good approximation. So the posterior really is Gaussian, but with a finite covariance.
Not in the infinite. So recall that convergence usually have the covariance. The standard deviation has a 1 on root n, so the scaling, and the covariance has a 1 on n scaling. So if you so that corresponds to me saying sort of zooming in far enough. But so if you scale the variance by n, then yes, there is a fixed value in which the asymptotic asymptotes to that value. So that is just the usual central limit theorem. For example, what is that? The central limit theorem approximation to the binomial. So if the number of binomial trials become very, 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 very large, what I'm saying is not very different from that situation, right? So the binomial is a discrete distribution. It's not, that's actually a good example. So the binomial is not only a discrete distribution. It is zero for negative number of trials, right? Sorry, for negative number of realization. It's only positive at there. But if you put a normal approximation on the binomial distribution, it means that like there is a non-zero probability that I I get -3 number of heads or something like that. That's impossible for the binomial, but possible for the approximation. But as n, if you crank n up enough, that normal approximation, and if you crank n up enough, the binomial starts to look like concentrate around the mean probability, and the normal approximation becomes very, very sharp there. And even though it is wrong at the negative part, it is wrong in a diminishingly small way as n becomes larger. Similar things is happening here. Like far away from that neighborhood, it is wrong, but as n crank up enough, the difference in the distribution, it becomes less and less important. In fact, exponentially less important as you go far away enough from the neighborhood.
Okay, thank you. I'm good.
No.
Someone had a question?
Presumably yeah, I don't know, no question. Just verbal diarrhea. Like the neural network used to learn the resolution map. I mean, you're careful to. That's not singular with its own resolution. I mean, I just wonder. It seems these resolution maps are so intractable and difficult to access and maybe even understand. I wonder if the neural net gives you any insight into the resolution maps in general. And,
that's a really
their form.
Question.
Yeah,
Yeah,
that's a pretty. Yeah.
I'm just
at least
using,
I don't have an answer.
Yeah, I'm using these affine coupling layers. It's just a simple architecture. It's easy to fit. I did not really think very hard about, really how to design the approximation of the resolution map. There's something very hand wavy in the preprint where I'm just arguing that if my neural network is expressive enough, I'll I can learn the resolution map, and then the theoretical guarantees I enjoy for the resolution map will be inherited by this approximation. But I've not really thought about it very carefully. I think that a good future work would be just somehow baking in some knowledge we have about how a resolution map actually what it looks like. But I don't know. I really don't know.
Let's be clear that learning the resolution map is in some sense ill-defined because there is no the resolution
That's
map.
Right.
Yeah.
That's right. But certainly this map that I'm using has a upper triangular Jacobian, which is really quite restrictive. And there's a part of me that worries that no resolution map has this type of Jacobian structure.
Mm-hmm.
So,
Dan, did you Dan, you said when you said you can't learn the resolution map because there isn't one, you mean there's not a unique one?
Correct, yeah.
Okay.
So you could certainly learn a resolution map in principle. Lots of questions. It's very...
The sort of logic...
Go ahead.
Sorry. I want to say that the sort of logic that this is relying on is that if we have a large enough, expressive enough neural network, so that a resolution map is included in the family, then at least we know that in that variational family, there exists one distribution that achieved that asymptotic, that achieved that matching leading order property. But there are certainly other distribution in that family that could be even better. So at least we know that the gap is at least not growing asymptotically in log n, for example. That's contingent on the neural network being expressive enough to approximate some resolution map.
Yeah.
Maybe I missed this. What do you mean by having the neural network approximate the resolution map?
So the logic is, if we have a resolution, if we are given a resolution map, we use that generalized gamma family, we get good property A, right? Okay, but we are not given the resolution map. So let's use the neural network to approximate it, and to approximate that resolution map. So that if the neural network is expressive enough to include some resolution map, then we get good property A.
I see.
Yeah.
But basically, our theory is for a variational family that's defined using this unknown resolution map, or an unknown resolution map. But because we have to, I don't know, use the variational family somehow in practice, we just chuck a neural network instead of the unknown resolution map.
I see.
Other questions for Edmund? Comments?
Very cool. Thank you very much.
Yeah. It's such a cool idea. We'll forgive the preliminary state of affairs because learning resolution maps surely was never meant to be easy.